Hi, all. Hi, folks. My name is Angela, and as I already said, we'll be facilitating this meeting today. We'll be diving into this excitement world of software 2.0. So, with our amazing speaker that we have today. So, for those of you new to AI Expedition, we are a community with a mission to make learning about AI fun and easy for everyone. So we believe AI shouldn't be a mystery, and we are here to build a community where everyone can learn, grow, and be inspired by AI. A few housekeeping items to keep things smooth. Feel free to add your comments and questions throughout the webinar in the tab. You can also use the reaction features to share your feedback, a thumbs up if you are enjoying it, that would be great, or a question mark if something needs clarification. If you have any presentations, feel free to use the raise hand feature. And yeah, that's it. Okay, today's topic is software 2.0, the mystified, I don't know if I'm saying good, a strategic overview for AI projects leaders and AI delivery management. In this webinar, I think we are going to explore this shift from traditional software development to this new paradigm where AI and machine learning playing and steering role. So let's continue with our speaker, David Cardoso. Wait a minute. It's my pleasure to introduce you, David. David is a machine learning scientist and technologist with a passion for leveraging cutting-edge tools like JaxFlex and Docker to build impactful products. He's also a Google developer expert in AI, an active contributor to the machine learning community as well. So, hello, David. Now I will pass the floor to David for his presentation. So take it away, David.
All right. First of all, thank you for the invitation. Since we are on the chat a small group, I'll invite everyone that if you want to interrupt me, go for it. If you want me to go into more details, I'll do it. And yeah, so today talk is mostly I usually, or I was telling Maria that I usually prepare a lot of very technical talks. I really like that, but there is a part that I always think, especially with people that are trying to manage this kind of new roles that are appearing, like people that have to manage machine learning engineers, people that have to manage data scientists, labelers, and what I wanted to show is. This is by no means like an academic definition. This has been something that has a reason mostly for the industry. There are still debates of how to define these boundaries, in which what is actually software 1.0, software 2.0. And I wanted to bring some personal experience. I think that what I can bring you guys is that I have committed a lot of mistakes in my professional life. I have made database on productions go down. I have put a robot on fire while deploying to university campuses. I have deleted financial information from tax documents. And I think that all of this is to show you that this is the way that has allowed me to at least reduce a little bit, just a little bit, the amount of mistakes while working with people that are machine learning engineers, data scientists. So this is very experimental, and what I would love to have is that you guys could enjoy this talk and then say, okay, so yeah, so what I'm going to do today is, as I told you, I was going to define what the hell is actually software 2.0, and most of it is just to give you an aesthetic overview, like if you have to deal like have management roles or leadership roles, and also like give you a glimpse of actually from my consultancy, how we actually manage this kind of projects. So as Angela was telling you, I'm David Cardoso. I'm chief analyst for Updata. We are a consulting company in the center of Quebec. We do a lot of computer vision optimization, computer vision, and mathematical programming. If any of these subjects really interest you, just hit me with a message, and I'll be happy to give you to give you a tour of what we do. So to start the story, I'm going to go a little bit back on time. I'm a historian by heart. Like uh, my school, I try to do a lot of history courses. So we're going to go back to 1 million years. So alongside the development of human civilization, well, we got the gift of fire, right? So um, there is the Greek story about Prometheus that is taking the fire from Zeus in Mount Olympus. I'm a very historical guy, so there's going to be a lot of historical reference and mythology. And it is said that that the reason that this titan stole the fire from Zeus and gave it to humans, and humans got the gift of fire that allowed them to not move alongside the world, but just to create community and everything. So the analogy here, or the story that I wanted to bring, is that we got the gift of knowledge, right? We have the gift of learning how to do stuff. The gift of intelligence. It's part of this analogy of like getting the gift of fire. And over for 1 million years, so we discovered fire. Then as a team, we decided to, as a society and civilization, we decided to do agriculture, hunting together as a species. And mostly has been done that hard work requires a team, right? You cannot do it all by yourself. As a very cliche or motivational quote, if you want to go very far, you go with a team. If you want to go very fast but alone, you're not going to get very far. So hard problems requires team efforts. And alongside with it, we started to see that we need to observe nature and to observe patterns of nature. And we discovered the mechanical computer, the analog and mechanical computers. So I don't know if anyone knows what is this image. This image is the anti-theta mechanism. So it was a machine developed by the Greeks to actually find stars on the sky. So it was kind of not a navigation, but just to track, okay, if this star is in this position around this night, in 2 days or 3 days. And yeah, so literally it's a model that in which you put the inputs of your star, and then you put the calculation of how much in time you want to see these kind of stars. And yeah, this is the start of the analog computing side. And then we discovered electricity, and the first computers and the first programmers started to appear. So here is the ENAC, the first machine that required a whole building to power. And what you can see here are the first programmers. So I don't know if you know, but most of the computer science at the beginning was a woman field. I don't know where in that part we changed, but I just wanted to show that historically Ada and the first programming technicians were actually women from the ENAC party. And then finally we got to 2010, in which now we have a very strong computer in front of. We are probably looking at this lecture in front of a computer, and we require developers. So what happens when we have developers?
Developers, 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 developers. Developers, 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 developers. Yes!
So Steve Ballmer, quite the guy, CEO of Microsoft, I say, with this new role of a developer. Most technologies is just the man that can turn coffee or in my case, water, coffee into programming language. And the whole idea is that now we have to develop a new way on how to tackle problems. When the developers start to appear, we alongside the humanity or alongside the human civilization, we see that we tackle problems by decompose a little bit. So what we do is that, okay, I have a problem. I have, for example, I want to communicate one computer to another, so I can identify that I don't have like long enough connections to do that, or I don't have a protocol to define it. We break down these big problems into very, very small problems. And for each individual problem, we design clever algorithms to solve this problem, and then we compose this part, and this is what we call the stack. So what we can see on the screens, so if this works, laser pointer, yes. So what we see here is that for people that know networking, so the TCP IP stack is so you have network connections, you send packages by the application, you give it to the kernel connects with the hardware modifies this into zeros and one, then sends us to the cable receives it, and you decompose this kind of problems and you define a stack. More in the more modern sense, the AWS stack. So if you can have a service that has computing as a service, or you create ES2 instances, or you want to save files, so you use S3, or if you want to use a database, you use I forget the AWS stack, but the same thing happens in software in the mobile development, right? So if you have an Android software stack, so you have the Linux kernel, you have the Java API, and then at the end you have the application, the thing that you have on your hands, that everything. So when you this is something that has been proven ages and ages every time, and is that you decompose the problems and then you just start to see it. And the only thing is that this not only works on science, technology, and engineering and mathematics field. This also is like how big projects have been done. I'm a fan of movies, so I really love how you make. I really love to see documentaries how movies look like. So you can see like you need to define the script, what is the story, find the editors, then define the cast crew, then the film, then you take the script. So you clearly decompose this kind of problems. And for those that probably here, there is many of you that are project managers already. This implies, sorry. This implies that in a more academic settings that you have what is called the B model for implementation. So you define with a project definition, you define the concept of which operation I'm going to tackle, what are my requirements, my design docs, the architecture that I'm going to take, then detail design. So how is going to be the implementation details? What are going to be the tests, right? Then I have a proof of concept. This proof of concept implies, okay, do I pass the user settings? Do I pass my machine settings? Do I integrate correctly with the system? Then I system verify and validate. So you create your, I don't know if you are developers right now, but you create the test, things that I don't do, I don't know that work, but you create the test, the integration test, the unit test, the functional test. Then you operate and you maintain. And this goes into project definition to project test, and then verification validation. You go back to, okay, this part of the project is out of scope, it's in scope, or do you need to go back to parts? So this has been like the most used framework for solving problems, and I think it's the one that is being taught over and over in any engineer career or computer science career. And it's not bad. I mean, for a while we have been created very, very specialized stuff. So for those who don't recognize this image is a wafer. So try to explain this to the people of thousands or 2,000 years ago, that from sand, for pure sand, if you put enough pressure on it and then you pass a little bit of electricity on it, you can have a computation that allows you to do zeros and one, right? And this is one of the marvels of modern technology. The connection between internet, like being able to communicate information that pass, like if you have a tense situation in one part of the world, gathering information to the other side in less than 10 seconds. something that it's very like it took us less than 100 years to do it. And also computer graphics. I don't know if you guys have seen, especially the development of video games and movies. We're quite crossing the boundary of realism, and it's part of this framework of decomposition that allows us to to make very very useful stuff. Now we start to see, or what we start to see is that not every single problem can be solved by this decomposed stack. So the first problem that I want you to bring you guys is that I have a picture here on the left that is the image of a cat. So this cat, uh, if you open this on your computer, the computer is what's going to read is going to have a file that has that is going to have a representation of a matrix, and this matrix is going to say, hey, in this point, the intensity of the red pixel in that part is very bright on red, zero on blue, zero on green, and then you specify by each of the points the image, and then there is software that is going to say, okay, I'm going to take all these intensities, all these colors, and recall from your uh, primary school that you can do any color with the composition of three colors, red, green, and blue. And what we decide is that what we have found is that trying to uh, make the computer understand what is in this image is very hard. So I will put you to the left, like in a programming language, how you actually go through each of the pixels. So you go through all the pixels in the row, all the pixels in the column, you gather the information, and you say, okay, which is the intensity of this part, and then you give it to the screen. So it's the 1980s and the 70s. We started to ask, hey, how can I make, or how can I figure out that that tell the computer automatically, hey, this is a cat. Actually, for us, it's a very simple task. I'm going to do an asterisk on that last observation, but it requires a baby 4 years of just input on images to say, hey, that's a cat, right? Or hey, that's my dad. Hey, that's my mom. Or hey, this is dangerous or not dangerous. So we don't know how that process goes, but we alongside the 80s and the 70s, we were trying to do a lot of how we can actually implement that into a computer. So, for example, I'm going to give you, this actually was a PhD thesis in the 70s and the 60s in the University of Toronto and MIT, is that, okay, given this image, you apply a transformation, which is a Sobel filter. In details, what a Sobel filter does is it just takes the information of, you take a pixel, you take their boundary and say, okay, is this the pixel that has most intensity? It is, okay, so I will just pass it. If not, then I'll go to 0. And then with that information, you can create in all the channels where is the most intensity, and continue, and then have and then have that information and just put only one channel in which, instead of pixels, you only have the intensity of light at that point. So you have here 0, 0, zeros, and then you're going to see that on the boundaries you have ones or close things to one. And we figure out that maybe, just maybe, if you learn these characteristics of the image, you can actually say, hey, maybe the image have this kind of two eyes, this little nose, and this kind of ears, you can say that that is a cat. And that's what we try a long time. People went to grad school to learn to try to put this kind of rules. Okay, if this a cat, given this Sobel filter, has this kind of ears, this kind of eyes, this kind of another ears, and then I collect this information about all these kind of filters, then I can say, hey, is this a cat? And what we encountered is that it was very, very, very difficult. If you want to see what was the things of computer visions in the 80s, you can see the textbook by David Marr called Vision in 1982, and his whole project, or the whole goal of his lab, was to actually identify humans in an image. So what they did is that, okay, a human is most like a cylinder, then a composition of cylinders, a chest, head, arms, and try to put these kind of rules of how they look like. And they try to say, okay, in the most simple example, like what if we try to identify a cuddle bear? So okay, try to figure out the depth, how the gradients look and that, and then try to get all this kind of information. And this was done at hand, so it was very difficult, and it just only from one image. If you try to move this kind of image, as soon as you move another image, you have a completely different image. And this was very, very difficult, and this doesn't scale. So just to show you that probably I'm already in some CIA list, I put single cat photos, and all of them, you can see that there is variety on the color of the cat, on the type of the cat. Also, there is cat that has glasses, which I guess you don't see that much a lot, and there is also humans in the picture. So try to put rules that look like this into rules that put like that. It's extremely difficult, and this doesn't scale. So what we usually, or what we saw in the history of science, is that whenever you have a problem that is that seems to stop, what kicks the innovation, or what they put, what we put in oops, sorry, oops, what we put on like the stick for innovation, is try to look what other areas are you are looking at. So Hubble and Weasel, they were two scientists. I don't recall if they are, if they were American or British, but what we're doing is that how actually the brain process images. So what they did is that they create a monitor in which they were given things like lines, circles, square, and then they open a little kitty head with the mystery, and they put some cathodes and try to find the electric signal. What happens when you have a zero image, and then they give the stimulus. And what we found is that apparently is a hierarchy processing. So what happens is that the image goes back to your head into the what we call the B1 post-frontal cortex, that image. So get some information about what are the rules. So this one was extremely activated when you give only like a line, circle. When you have like squares or things that are composing of lines and other circles, it activates your B2 and B4. And more complex images start to go to your IT cervix. So what happened is that apparently simple information, it gets activated on the B1. Then as complex images start to appear, it start to propagate that information. Okay, in the first filter, you kind of learn that there are only lines and circles, but if it's a more complex image, you activate this kind of part. So it looks like natural images are hierarchical in information. So this is what actually gave the explosion of computer vision in the 90s. So what we say is that, okay, if I need to do hierarchical information, what I'm going to do is that I'm going to take my images, I'm going to do a lot of feature extraction. So I'm going to do what you do in your computer statistics class. You're going to create a support vector machine. You have examples, a lot of examples that of images that you want to classify. You do support vector machine. You can actually decompose with principal component analysis and that was very limited. Again, we start to see that even if we try to find what are the more general image statistics, it also doesn't scale. It was extremely difficult to find a general part. And what it kicks out, or is that actually somewhat at the University of Toronto, a person that was the student of Hinton, a professor at the computer science department in Toronto, actually what it says that what if instead of doing a lot of feature extraction, in which I try to create a lot of statistics to show the machine, I just tell the machine what is the skeleton of the image, like what is I give like a kind of a skeleton of what should I be looking at the image, and that then let the machine figure out their own rules. And this is actually the kickoff of the deep learning revolution. So it was someone that just said, okay, I'm going to take a step back. I'm going to say, I'm not going to do anything of this feature extraction. I'm just going to tell a machine, hey, these are my images, these are my data. And what I'm going to do is that choose whatever parameters that you want to find. So yeah, I will tell you how good or how bad are you at this task. And if you are very, very bad, you can modify your internal state, so you can modify, so you can be better at the task. So what we find out is that if f is a differential function, so that is to say is that you can take the derivative of that. So you know that if a function is differentiable, you can take the gradient. The gradient will tell you the direction in which it will augment the most. And if that function is the function of the loss, you can take the minus, and then it will go into the direction of reducing the loss. And this is kind of the start of what the whole thing of machine learning is now in the last part. So let's go back a little bit. This is going to be probably the 2 slides more technical that I will put here, and is what is exactly a neural network. So we took the experiments of Hubel and Weaver on the cats, and we figured out that neurons are just a connection of activations. So if you put a little bit input here, the thing is that it's going to do a very simple operation here, and then it's going to activate something alongside. So you have your entries x1 to xn, you get this transfer function, and then you pass the output. And finally, what you're going to do is that you're going to call these little neurons, you're going to put it into a layer, then you're going to create another one that have layer, and then you just create the number of neurons that are here and here. How you choose the best architecture, you let the machine figure out. There is a little bit of black magic that happens in the machine learning side, that the only way that we can find is to treat these algorithms as a black box, and then you repeat the experiment. What happens if I change three neurons in the input layer by 4? What happens when I change a hidden layer by 4 by 5? So what we do is we apply the scientific method. So we set up the experiment, we validate, we say, hey, what happens if we add 5 neurons, 6 neurons, or 2 neurons? And then you start to see if there any correlation with the number of neurons and your performance on your task. And what we have found is that if you put a lot of hidden layers, that's what we call deep learning. The learning is extremely good at very large tasks. So I have an example for you. So take a look at the image on the right. And the image of the right, what I did is I took some data of a scientific experiment that I wanted to figure out. And then I'm going to try to find a model that actually adjusts this data. So as you can see, hopefully everyone can see that this kind of function of the points look like it's a straight line. So what I can do to the machine learning algorithm is say, hey, I believe that this is a line. So the line is characterized by 2 parameters, m and b. So I'm going to give you, choose m and b as you want. So in this case, the machine took -8 and -8. I will tell you how good or how bad are you with the error, all right? And then you figure out what is the best line that adapt to this data. So as you can see, this is the loss, the function of the loss function. So as you can see, this is a convex function. So recall from your math class that optimization and a convex function always have a minimum. Long story short is that there is going to be a solution. In machine learning, here we have 2 dimensions, and we can see this, but we often deal in machine learning with input data that has n equal to 4,000, 6,000, 12,000. So it's difficult to see, but as scientists, as engineers, so we take a very small example and we figure out. So you see that if the machine took -8 and -8 at random, it's going to have that the error is 370.7. What is the error is the mean square error, but assume that it's a number that I can give you. So now what the algorithm is going to do is it's going to say, okay, so I know that I was very wrong with -8 and 8. So I can do is I can take a step on the negative of the gradient. So what's going to happen, if you recall, if you had any vector calculus, that in this point you're going to calculate the gradient is going to tell you that if you want to augment this function, you go to this kind of direction. But if you want to reduce it, you just take the negative and you go like that. And this large step is going to be called the learning parameter, but this is going to be tackled by different algorithms. But the important thing is that I take a step in the direction of the inverse gradient. So here the machine say, okay, I'm going to try 4 and minus 4 and 14, minus 4.14, and then I'm going to take the other parameters minus 5 and 83. You see that it's not the correct line, but we have reduced the error. And what is going to happen again is that he's going to move minus 1.1 and minus 410, and you're going to see that the point is get moved. Finally, we start to see that the point is getting close to this kind of a small minimal error that is going to happen on the data set. So here minus 18 and minus 1.61 for the bias. We reduce minus 12 point. Yeah.
Sorry, quick question. Like if we were going to put this into perspective from a business perspective, like have you encountered a project similar to it? Like how would you describe this problem? Like if I don't have any technical background at all, if I have never taken any math class, how would I look at this if I were a project manager?
So as project manager, the whole thing is that I'm going to tell you again. I'm a guy that tells stories. So in my consultancy, sometimes you go to projects in which people have done this, apply this kind of I don't know, algorithms that they want to identify phases for security. So we were working with a company that you wanted to automate the entrance to a bar. And what we have found is that when people start to use this kind of the shelf solution, they were having very a lot of mistakes. They were denying the people that needed to enter to that. And I recall a little bit that I said, show me your baseline. What is the most simplest explanation that you can have? And when we try a linear model, we beat their state-of-the-art machine. So long story short is that linear models should be like in your toolbox always. Most of, like, as a physicist, I will tell you that the most of physical nature models are just linear. So always probably as a project manager and everything is that if it should always give yourself that if you want to experiment on some data and you see that you want to model certain stuff, you're going to see that linear models are always a very good one linear approximation. So I think in the business and everything, recall mathematics is like a toolbox. So whenever you find that you want to predict something, you can always assume first that it's linear until you're proven wrong. And I always tell the story because people start to throw problems like that. Oh, we're going to do machine learning sites. Don't let, especially young developers or young machine learning engineers that said that you give the data and then they say, oh, I'm going to throw this everything, gradient boost, I don't know, what is the hype now, machine learning, artificial neural networks. Sometimes ask them, hey, can you show me a linear model to see how bad or how good it is? And you'll be surprised sometimes. Linear models that there is a philosophy about that. Sorry, just if I want to expand a little bit, is the open razor. So the open razor says that probably if the most simplest explanation is the one the most correct. So always try to model nature as linear.
I like that. So this is not going to be recorded.
It is recorded. So
it is recorded. Yeah.
But as a scientist or as a physicist, you always say, okay, let us do in a very small area linear, and you're going to see that you always have it's always a good idea, especially when you have very young developers that want to throw to the best or the biggest model there is, or to use LLMs to that, is that show me a linear model. I think that's the best advice that I could give.
That's a great takeaway, because I've seen in a lot of our businesses something similar. Like there's a new LLM coming up and everyone goes behind that new shiny toy and they think that's the best for everything. But in reality, you really need to check what's your business problem and see what fits best. Okay, so bottom line, for all the project managers or aspiring project managers or anyone who wants to work in AI, look first at linear models or have it as an alternative, basically, depending on your business case. But okay, thank you, David.
It's always important to have a baseline. So always ask your team to have a baseline. And actually, I can give you, there is another part that I have done in my job. It's real estate prices in Canada. I know it looks exponential, bear with me. But if you take 1990s to 2000, you're going to see like very linear models to that. And people try to do a lot. I don't know of you, but there is a lot of speculation on real house development, and people like, if you take a look at the story of Silo, the startup that was trying to take picture and try to accumulate that, sometimes they were beaten by just a linear model. So again, the simplicity of the Occam razor in machine learning is always very important. Anyhow, so yeah, so long story short, you can move on that part, you get to that part, and then finally you get a model that more or less is very accommodated to the data. You will think that this is very simple, but I wanted to show you. This was a recollection of me driving in a virtual setting through a part. I collect the image, I collect what was my input to the data. I collect that, generate a model on that, and there are parts I was doing very good. I didn't show. Here is not the video that I want to show. The video with the linear model is very, very bad, but it learns something. It's able to gather some information. So this has a more complex approach, but I will try to find the linear model afterwards. But the linear model also do certain things, right? At least in a very short time delta. And this brings the machine learning paradigm. So it's always put an induction, a bias induction on your data. If you think that is linear, or if you think that has, you as a project manager or strategic have something that the developers don't have, is that the knowledge of the field. You already have seen this data. You already have seen how things work in the real world. You might not have a model of that, or your brain cannot put this into words, but try always to that your models. And that your models follow your intuition. Our intuition is not that bad in many of the cases. So the machine learning paradigm is always make guess, measure accuracy, optimize your guess, and repeat. Finally, there are many things that you can do with that. So just a small sample of projects that I've been working on. It's you can do a space, free space for robots. Um, Recycle, like here in Quebec we have a machine X that controls separation and triage, recollection of trash on that, and these are things that are run all over all over the world. So long story short, so we're 1.0, in which your code, your rules, and everything just allowed you to have a very, very small percentage of the program space. What you can do is always with software 2.0 is that you let the machine figure out to search for the best for the best state for the program. So you, with software 1.0, you set some rules, you program. It's going to give you it's going to give you that it's going to work on very specific scenarios. Software 2.0 said, okay, this is probably where the solution is going to be. If you have an optimization mechanism, you can let the machine try all the inputs and outputs and figure out which is going to be the best the best solution that you can find. So it's the whole takeaway of software 2.0 is that machines have time. You do not let the machine try and error a lot of stuff, and then you just charge the big bucks, right? So quick recap: software 1.0, or decomposition by engineering, is explicitly engineering system. Software 2.0 is about finding programs through optimization. That is direct search using training data as the guide. There are a lot of limitations. I want to have, so this is part of a comic that is called XKCD. So as you can see, there's a guy telling this is your machine learning system. Yep, you pour the data into this big pile of linear algebra, then collect answer on the other side. What if the answers are wrong? Just steer the pile until they start looking right. So it hurts to say, but there is a little bit of true on that. So you start to see that, and yeah. So the most general part that you should take is that software 1.0, you take rules, you take data, and then you give answers. And finally, from the machine learning side, you get answers, you get data, and the machine learning will figure out the rules. So instead of answers, you get rules, and then you apply those rules in what we call inference. software 2.0 is not an idea from me. It's not an idea from academia. It's actually from a guy called Andrzej Kaparty, who is actually a University of Toronto graduate, who was the chief technology officer of Tesla from 2016 to 2020 21, I think. And it's a part that you program from data, accumulate a nice and very large clean data set for all the different tasks, and worry about the edge case and messaging is where the most action is. So you accumulate data, you show examples, you create this database of huge amount of what if scenarios that you let the machine figure try to find the patterns. So again, Car Party, Twitter. If you are using Twitter, follow him. Very, very smart guy. That great in the sense, the algorithm that I show you, in which you were going down a little bit, can write code better than you. And it's not that it's that was 2017. 2024, I think if you take a look at Copilot, Chat GPT, and everything, uh, at least for me, you can write much better code than I do. Yeah, I can give you the part. I think I can give you the creativity and everything, but my unit tests are written by this. So uh, mostly that there is also like a huge warning that you have to that. When you get your machine learning developers that are very juniors or like software guys that are very dependent on the skills, always it's important that you try to always figure out that people have their bases correct, that they know how to architecture systems, that they know their programming very well. Uh, ChatGPT and Copilot can help you a lot, but you also have the responsibility as manager of when things go good, it's because of your team. When things goes bad, it's because of you, right? So always have think into account. And one of the warnings is that especially with the new wave of developers, always make sure or try to develop areas in which they don't they don't they are not dependent on those tools, but they can manage, they can leverage these tools. Is that what I want to say? um the example is that for a while they were doing this kind of thought, this that how do you identify that the car is parked. Then they have this YOLO algorithm, or this object detection algorithm. There's a car, and then they put the rule of track bounding box, and if it does not move more than 20 pixels over the last second and is a neighborhood, and they put a lot of rules. This is software 1.0, and what they did is that they rechanged this whole system by just, hey, I'm going to have data, and then if the neural network says so, that they collect a lot of data, it's a park, it's a car park. So again, here rules that you put as a human, you might be even missing some cases. In the right, if you have enough data and large enough variety of data, you can actually do the tasks very, very well. Yeah, so collecting data. What I want to see here again in my example, I was taking a computer. I was playing video games on my work. Yeah, actually, I guess that I, 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 I was playing video games at work, but yeah, recollect data, save those images, save those actions in some database, and then act on it. So how does the 2.0 stack looks like? Like when you talk about 1.0, you have programming IDs, Visual Studio Code, bus databases, Cloud SQL, Postgres, and everything. Like how does the 2.0 stack look like? So the first thing is that it kind of breaks roles on data teams as two, as labelers and machine learning scientists or engineers. Just be careful. The word engineer in Canada is protected, so that's why you're going to see that people call machine learning scientists in a lot of titles, because engineer is a protected word. But the roles are very take data, create models, and people that do annotation. And sometimes you as a scientist or as an engineer, you have to put the role of looking at this level. So first one is CVAT if you're working with a lot of computer vision. So things that you can put, hey, I want to put a bounding box here. Hey, this is an image. Hey, this is a segmentation. Hey, this is a part. How many points to actually tackle this kind of part? And then you recollect the data. You create pipelines that allows you to learn from this data. So CVAT is one of the part. Uh, don't let you there is part of you need to deploy models. So this is not true a lot. I don't know in companies in Canada, but I have seen this a lot in other countries, that Sometimes you have a model that it took 3 weeks, and then it's been more than 1 year, and the model is still not deployed. So it's important that you can actually deploy, because launching a model is easy. Operating is hard, and most of the problems that you're going to find in a machine learning system will be when you are continually operating for the long term. So for example, I was consulting for a company that they have the application for identifying interesting objects in an image. And what they figured out is that even when they trained the model was very, very good, when a year passed, it was really bad. And what we find out is that the distribution of the images taken with new pictures, new iPhones, new Samsung, is that with the higher quality, the distribution of the pixel in which we learn the data was changing. So it's alongside in a continuously operating that machine learning models start to appear. And mostly it's recollected in this architecture. You have machine learning code, you have data collection, you need to verify, you need to monitor, you need to do analysis on the monitoring data, you need to process data, you need to do this research, you need to extract some features, some statistics. What is the distribution of your data set, the median, the standard deviation, and what is going to be your serving infrastructure and the configuration. If you're interested, there is a paper called Hidden Technical Debt in Machine Learning System, presented in NeurIPS 2015, that actually provides a good academic overview of what is this part. And then mostly the challenge, apart from a production side that is scalability, availability, portability, is that where this data comes from, who is owner of this data, who can access this kind of data. Can I continue train on this data? Can a person that decides to launch a job is going to do it easily? Is going to be able to do it, to select some subset of the data? What happens when the train and the service does not start to drift a lot? What is you can validate, which is the model analysis. And what they have found, at least in Google, is that an even research, where you put your engineers, your scientists, and the researchers embedded on the same team, it helps to reduce this friction of launching models together. So as a manager or as a business partner, always have that your team, the guys that do research and the engineer, always are like hand to hand working. And yeah, there is a paper called Rules of Machine Learning paper, which also gives an overview of what are actually the rules when you do a lot of machine learning, and always know what are the requirements, the freshman requirements. So this is, I think I can do it here. I cannot put text, but anyhow, here the Frenchman requires that sometimes what is the delta time that you need to have a new model? What happens? So cats and dogs. So if you are trying to generate a model that separates cats and dogs, it's cats and dogs are not going to change, at least for the least thousand years, right? But if you're working in a financial scenario in which stocks and volatility change every single second, so do you need to retrain a model every minute, every second, every 500 years? So always know your French requirements, and always plans launch to iterate. It's better to launch and to see what happens and then iterate. Not to give a little bit of a sponsorship, but I was one of the Kubeflow liaisons manager for pipelines. So it's a machine learning it's an MLOps framework, so that allows this kind of stuff to be done easily. So create models, repeat this process of figuring out the statistics of the data, and it's served via GCP or via Kubernetes. So yeah. If you are interested to have your team that always be able to retrain models, and to do that, you can use Vertex pipelines and Kubeflow. And then yeah, that's I know that was a lot. That's for me. What's next? So hopefully, if AI takes my job, I will be able to do my classes next on the fall, the fall of the Carthaginian empires on the Punic War. In the meanwhile, I will have to keep doing technical presentations. My name is David Cardoso. Add me a link if you find this interesting. If you are in this kind of part and you want to, I'm always open to a message. I might not reply instantaneously, but I'm always eager to have a talk. So that will be for me. if you have any questions, doubts, observations, feedback, I'm really happy to receive those.
Thank you so much, David. That was very insightful. So now let's open the floor for questions. If you have any questions for David about software 2.0, please feel free to type them into the tab. I'd be happy to read them.
I do
So
have one question, if
great, Andres.
you allow me. Yeah, what is your recommendation? I was checking today, LinkedIn was populated with a lot of noise about Meta new model, the 3.2. And it has some small models that can be used also for multimodal use. So that means that it can be used also for image recognition or for object detection. Like, what is your recommendation in case of speed and also in terms of cost for starting a project in AI? Like, should we go for a custom model that we train from zero, or we can go for those LLMs? What it should be the first approach?
So it's always I'm going to refer again to the part that says always have a baseline. Like what I will do is that always try to make what a linear model, try to take something that it doesn't expand. Like what I have seen, especially with companies, that they always try to go to these kind of LLMs, big LLMs, multitask LLMs, and sometimes doing this kind of inference on these models can be very expensive, right? When you send things with Gemini or with or with Chat GPT, it has the same structure with in cloud computing. At the first, you say, "Hey, this is very fun. This is very not that expensive." And what happens is that when you scale your project, and if the project requires scaling, you get hit with a bill of 2,000, 4,000 just for one day, right? So my always approach has always been, and the part of what I always want to go to this software 2.0 is always create a baseline. This is create your guess. Does that work in your scope? Does not? Okay, let us go to these kind of models, but try to always quantify how much I'm getting, how much I'm winning, or how much what is the space of in French they have this word of marge de manœuvre, which is a margin, like a space of maneuverability, in which, okay, your baseline and this kind of models, what does it provide you? And especially now with the LLMs that are not running on your site, always take into account the price to do the inference. So my approach has always been is get requirements, see the data. Does a linear model work, or does another baseline model works? What happens if I train on my site? What happens if I have my models? You might have also in the design documents that you create, you might have also the property that your data cannot go out of your servers or the country that you're training. So if you're inferencing with ChatGPT or Gemini, you might not have the right to send those data. Do what you need to do locally, and the structure is always going to be like that: baseline, scope, requirements, and then iterate, and then you close the cycle again of doing um, does this model work? Not okay, go back, retrain. If you need to retrain a model, maybe also instead of retrain you need to change the model. There is, I don't know, you saw that ChatGPT 01 is much better for the task at hand than the Gemini 1.5 that you always get recommended. So machine learning development right now is very cyclical. So instead of going back to implementation and detail, it's always analytics. Hey, how much I'm winning by using the model, how much I'm not. And if you don't have those things part, always have metrics to do this. So I don't know if that's the answer that you were looking for, but long story short, baseline, iterate, and go back to the scope and details. Don't fall into the trap of going into the first of going to the first model that helps you, because it's going to happen the same thing in cloud computing. You're going to get a large bill if you're doing this thing at scale.
Okay, thank you.
No, with all the pressure.
Thank you, David. Oh, thank you all for joining us today, and a huge thanks to you, David, for sharing your experience on Software 2.0. And as a token of appreciation, we like to present for you this certificate for your participation.
Thank you. Hopefully, it has been of some interest. again, I really hope to see more people in this area.
Yeah, okay. So before we go is a quick reminder that AI Expedition is dedicated to making an AI learning accessible for everyone. So we regularly host webinars and events on the AI topics. So stay tuned for our upcoming event and keep learning. And now we share with you our linking page and our new. So thank you as well to all our volunteers. And again, thank you for joining us. We hope you enjoy it and have a wonderful rest of your night.